So this is where we got to, and some of you I think had started this question and some hadn't. So I did say I would start today's lesson by looking at it. We're talking about here an arithmetic sequence. Don't forget, at the end of last lesson we went on to geometric sequences, so we're going to practice those today for the most part. But this was on page 82, or I can work it out, can't I? It's on page 85, and we've done a couple of these wordy questions for arithmetic sequences and series. And this was where we were drilling, and it cost £500 to drill to a depth of 50 metres. And then if you wanted to drill an additional 50 metres, you paid £640 for that extra 50 metres. So that's not the total cost, that's just for that extra 50 metres. Obviously the deeper you get, the harder it is, so that's why it gets more and more expensive. So what we have is an arithmetic series where the first term is 500 and the difference is 140. And we firstly had to work out the cost of drilling to a depth of 500. Now I have to say, when I worked through this one myself, I got it wrong firstly, because I worked out, I said, right, 500 metres will be the 10th term in that sequence. 50, 100, 150, 200. So I worked out the 10th term, which is the first term plus 9 jumps. But that's not correct. That doesn't give me the total cost. All that would give me would be the cost from drilling from 450 metres to 500. So what you needed to work out was the sum of the first 10 terms using our sum formula, which is n over 2, so that's 5, multiplied by 2a, and remember this is on the formula sheet so you don't need to remember it, plus n minus 1d. And I forget what that gives you. Oh, sorry, I do. It gives you 11,300. And in the second part, I didn't know the sum. Sorry, I didn't know the number of terms in the sequence, but I knew the total had to be £76,000. So it's unlikely that a sum of this series would add up to exactly 76,000. So I'm going to say, right, when does the sum equal 76,000? Knowing full well that I'm probably going to end up with n as not a whole number. So I get n over 2, which because I don't know n now, I'm trying to work out the number of terms. How many terms can I drill with for 76,000? But a is still the same, a is still 1,000, and d is still 140. And I always start, when I've got a problem like this, where I'm trying to find n with my sum of an arithmetic series formula, I always start by doubling, because that straight away gets rid of that n divided by 2. I'm going to multiply that bracket out as well, 140 times n. And double that is going to be 152, is it? And then you end up with a quadratic, don't you? So you multiply it all out, and you end up with a quadratic. So I'm going to skip all those steps. You end up with, or I ended up with, 140n squared plus 860n minus 152,000.
So I think 100 at the top, is it? Not 1,140.
1,000.
It goes 500, then it's an extra 640.
Right. So yeah. So that's the extra cost.
Oh,
so
right.
you're right. The total.
Yeah.
So I'm working out this. So the next one would be 780.
Yeah.
But the total of drilling to 150 would be those three added together. Yeah. Yeah. This, and when I solved that, I got n was 30.02 and n was minus 36.2, which of course is a nonsense answer. So I can afford for £76,000 to drill as far as 30 terms in that sequence. And 30 terms in that sequence would take me to 1,500 metres. So that was the answer to that, was to part B anyway, was 1,500 metres. That was how far I could go for that one. So arithmetic sequences and series are based around our three parameters, a, d and n, and our two formulas. The formula for a particular term in the sequence, sometimes called the nth term formula, and that's to get to any term in the sequence, it's the first term plus n minus 1 jumps. Don't be afraid to use your fingers. And then you've got two versions of the sum formula. You've got a plus l if you know the last term, and that was based on my party trick where to work out the sum of a sequence, write it down in reverse. You've got n copies then of the first term added to the last term. And then if you replace L using that formula, you get the alternate version. And that's all on the formula sheet. Actually, I'm not sure that was on the formula sheet. I can't remember, but certainly those two are. We then switched, though, last lesson. So that's for arithmetic sequences and series. We switched to geometric. So Friday's lesson was talking about geometric sequences and series, and with those we describe them, well, we still use A for the first term. We then have R, which is the multiplier, and R stands for common ratio. It's often referred to as the common ratio, and still have N. And so the formula for the nth term, you've got the first term multiplied by R n minus 1 times. And the n minus 1 is because to get from the first term to the fifth term, it's 4 jumps. So the fifth term is the first term times R, times R, times R, times R. So that's why it's n minus 1 times. And there is a sum formula which we will get to, should get to today. So let's have a little look in the books at some practice. We did, if you remember, at the end of last lesson, we did a number of examples relating to to geometric series and sequences. So we need to do a bit of practice now. So we're on page. Here we are, right. So we're on page 69 of the books. So I'm just going to do 4A, and then, because it was Friday, was a long time ago. So for 4A, I can see the first term, it's 2. I can work out R, and this was one of the key things, wasn't it, from last week? So work out R, you just take any term in the sequence and divide by the previous term. So it's 3. So the sixth term, well, I can either start at the fourth term and multiply by 3 and then by 3 again, multiply by 9, or I can just say, right, U6 is equal to the first term multiplied by 3 5 times. And when it says the nth term, all it means is that. Okay? So the sixth term, you can either say, right, that's the first term plus 5 jumps, so I multiplied by 5 jumps, or you can say, right, 54 is the fourth term, so I'll just multiply by 3 and then by 3 again. Either will give you the same answer. So 4, 6, 7, 8. I'm just going to say that again for the people who aren't sorry. So for C and D, it's actually 1 times that, isn't it? And 1 times that, because A is 1. But same thing. And C, because you've got a negative value of R, we get that oscillation between positive and negative.
Data sheet.
A maths formula sheet.
Well, a physics formula sheet.
Oh, did you leave one? Oh, right. No, there was certainly nothing in but Wayne taught here to you, so he may well have picked it up. Oh, sorry.
Thank you.
So R is the multiplier, common ratio multiplier, it means the same thing. So with 6, I draw a picture, no other way of doing it. Well, no, that's nonsense. But I find the picture makes it so much easier. So 4 times R cubed is 32, so R cubed is 8, and therefore R is 2, and there's no plus or minus with that when you're cube rooting. So it's no plus or minus. So the common ratio is 2, and that means that A has to be 1, because to get backwards you divide by 2, and then you divide by 2 again. Question 7, I mean again, you don't really need the algebra if you don't want to, but I'm clearly halving each time, but don't forget R can be negative, so 4 times R gives me 1, so that means R squared is a quarter, and the square root of a quarter is plus or minus a half, so if R is a half, then you get 2, 1, a half, a quarter, and an eighth, so an eighth is one possible value. But if R is minus a half, you'll get minus 2, 1, minus a half, a quarter, minus an eighth. So the two possible values of the 6th term are 1/8, that's if R is a half, and minus an eighth, that's if R is minus a half. Right, forgive me, I'm sorry that I'm pushing things along. We did an example like this one on Friday, although this one's slightly more obtuse, but it all revolves around the value of R. So if I want to know the value of R, I look at any term and divide by the previous term. Or I could have looked here and divided by the previous term. And the key thing is that R is the same. So those two are the same. So that is the starting point to answering part A. If you got that far, brilliant. That's your starting point for part A. Now I have to say at this point, I don't know why they haven't done something. At this point, when I was doing my working, I wasn't really paying attention to what the question said to show that. So I said, okay, normally dividing by x is a bad idea. Cancelling out x is a bad idea because x could be 0. but x can't be 0, we're told that. So I went like this. And then multiplied by 2 and multiplied by 8 minus x, which didn't give me what they wanted. So I had to back up and say, okay, I'm not going to do that then. Even though I can in this case, I'm going to stick with what they've got. So I'm going to multiply both sides by 2x. And I'm going to multiply both sides by 8 minus x. I'm going to change colour so this stands out a bit more. 2x times 2x is 4x squared. And that gives me 8x squared minus x cubed. At which point I say, well, that's a relief. Everything onto this side, add x cubed to both sides, take away 8x squared from both sides. Now, to work out the value of the 20th term, I really need to know a and I really need to know r, so I really could do with working out x. And this is a cubic, but it's quite an easy cubic, isn't it? Because I can firstly write it as this. And that gives me two solutions. This would be 0 if x equals 0, can't equal 0, so, or if x equals 4. So x must be 4, at which point I can rewrite the sequence. So 8 minus x, that becomes 4, and 2x, that becomes 8, and x squared becomes 16. So all of a sudden, this is a very easy question. So the value of the 20th term, well, that's going to be the first term multiplied by 2 to the power of n minus 1. So the 20th term would be that, which is a big number. Over 2 million.
You have times by minus 1.
I have not. No, all I've done is added x cubed
Oh, right.
to both sides and took away 8x squared from both sides, so I just moved it all over onto same effect, so same effect.
Yeah.
And then, is 4096 a term in the sequence? Well, it is if 4096 is 4 times 2 to the power of something. Actually, sorry. N minus 1, isn't it? So this is a problem with a missing number in the power, and so I'm going to solve it with logs. First thing I'm going to do is to get the power bit on its own, so I'm going to divide by 4. Don't really need the bracket there. George, how do I undo 2 to the power of something? It's going to be logs.
Yeah. Can you log 2 both sides?
You log to the base 2 of both sides, that's right. When I do log to the base 2, I'm asking, what power of 2 is that? That's what log to the base 2 asks. What power of 2 is that? It's 2 to the power of n minus 1. What power of 2 is that? Well, I really should know, but I'm going to get my calculator to tell me. It actually comes out to 10. So n is 11. Now, n is 11, which is a whole number. So that means 4096 must be an actual term in the sequence. We've done plenty of these questions where we get a value of n which isn't a whole number, meaning normally it's a sum question, meaning the sum never actually adds up to exactly that value. But in this case, because n is a whole number, I know that 4096 has to be in the sequence. And if you did have a look at question 9, I might come back to that log one because I really want to do the sum today. but you didn't need logs for part B because you work out that P, I don't know why they're using P rather than R, but P to the power of 5 is 200 times P to the power of 5 is 40, so P to the power of 5 is 200, it's 40 over 200, and then it's just the fifth root of that. I will throw that one in at some point, because it's quite an interesting question, but yeah, I want to get onto some today, so I can give you some independent study. So, can we move? So far, all our work with geometric sequences hasn't involved adding up the sequence at all. And when we're adding up a sequence, we actually call it a series. I think one of those questions actually used the word progression, which means the same thing. So, this is what we're going to do now. So, sum of and a geometric sequence. Now there was a nice trick for deriving the formula for the sum of an arithmetic series, and you are expected to sort of be able to explain that trick. There is not a nice trick for the formula for the sum of a geometric series. There is a proof, which I'm going to show you, but it's not a nice sort of party trick type proof. Let me give you the formula first, which is on the formula sheet, so you don't need to remember it. So if I know A, the first term, and R, the multiplier, the common ratio, and N, I can work out the sum of a geometric series. Yeah.
Do you know we don't have to remember the things?
Yes.
Do you have to remember it as a maths teacher?
Do I have to remember them? No,
Yeah.
they're printed in a textbook.
Oh, then you just remember them.
Yeah, to be honest with you, I probably have to remind myself of that one when I plan my lessons. So, but yeah, you rarely, once you're through your exams, have to remember much. Let me show you the proof anyway. So the sum of a geometric series looks like this. You've got the first term, and then the second term, which is a times r, and then the third term, which is ar squared, and then the fourth term, which is ar cubed, and that keeps going all the way to the end. And so the penultimate term would be ar to the power of, not a to the power of r, a times r to the power of n minus 2, and then you've got a r to the power of n minus 1. Remember, we stop at n minus 1 because to get from the first term to the 10th term, say if n was 10, you'd have 9 jumps. So that's the sum of an arithmetic. Ooh, that's not good. That's the sum of a geometric series. So what we then do is we say, okay, let's multiply everything in that equation by. Sorry, I might move to this. Let me write that again. Sorry. Plus ar to the n minus 2 plus ar to the n minus 1. Right, sorry. So I'm now going to multiply everything in that by r. So I'm going to multiply that by r. I'm going to multiply this by r. I'm going to multiply that by r. I'm going to multiply that by r. I'm going to multiply that by r. Keep going. I'm going to multiply that by r. At the moment it's r to the power of n minus 2, so it becomes ar to the n minus 1. And I'm going to multiply that by r, which makes it ar to the n. Haven't broken any rules of algebra. All I've done is going from here to here, multiply both sides by r. I'm then going to do this equation, take away this equation. And I can do that because what I'm doing is taking the same thing away from both sides of this equation. If I take away this, so if I take this away from this,
Okay, what are you actually showing us?
I'm proving this formula.
Okay.
Okay. Which is on the syllabus, but very unlikely to come up, so I don't want you to lose too much sleep throughout this. So I'm doing the top equation, take away the bottom equation. Sn, take away Rsn. Sn is the sum that we're actually after. And that's quite neat, because if you do this, take away this, look what happens. So that disappears, and that disappears, and that disappears. In fact, all you're left with on the left-hand side is that term, and that term. Everything else gets cancelled out. So you're left with A and AR to the power of n. So if I look what I've got here and factorise it, I've got s to the n times 1 minus r. And what I've got here is a 1 minus r to the n. Divide both sides by 1 minus r. You get that formula that we started with. Now, if that completely leaves you cold, then don't panic, because the formula is on the formula sheet. But it's quite a neat trick, isn't it? What we did is we did that formula, that equation, take away that equation, which doesn't break any rules of algebra because the equation at the bottom, top and bottom are the same. And if that was all a bit quick for you, you will find they go through it on page 71 of the textbook. So again, you know, that's but it's very unlikely to come up. So let's now practice using that formula. So can I get you to work out the sum of the first 10 terms of the sequence in A? And can you work out the sum of the sequence in B? You don't know the number of terms, you've got to work that out. You don't know the number of terms, you've got to work that out. You might decide to try and use logs with that. You'd be crazy. Use common sense to work out the number of terms. You know, fingers or list it out. It's not that many, and it's easier to do it that way. It's going to be big. It's going to be big. When you multiply to make a sequence, you get big numbers, and when you add those numbers up, it's going to be really big. And notice it's to the power of n, not n minus 1 in this version. So you get negative number here and here, but when you divide them, you get the same answer. So you should get 59,048 for that one. And for the bottom one, well, it's finger time. So I've noticed that it's minus a half that I'm multiplying by. So I've got to 128. So that's the 1, 2, 3, 4th term. So the 5th term will be 64, 32, 16, 8, 4, 2, 1. 11 terms. 11 terms. So and it's 11. And when you've got a value of r which is negative, make sure that you bracket it. So minus a half to the power 11. If you type in minus half to the 11, I'm not sure your calculator would do it correct. And on the bottom, you end up with 1.5 on the bottom because it's 1 minus a half. You're right there with that. So you end up with 683. They use logs, they're crazy. 683 for that. One more example. Oh, yeah, do it. It's high time we did a bit of logs. Start off by defining A and R. So with this question, I can either say, when is it greater than 2 million? But inequalities just, they're just too hard. So I'm going to say, when does it equal 2 million? And know that n isn't going to be a whole number, because it's unlikely that there'll be a value of n that gives you a total of exactly. So I know I just need to go up to the next one. Yeah, they're not allowed to go 8 minutes early.
What are you doing? It's not.
Right, boys, go quietly, all right? I'm trying to get on with our work here. Let's go quietly. Let's go quietly.
Were we that annoying when we were year 7?
Just year 7, George. Right.
He's quick, isn't he?
So I'm going to I've spotted a log problem. Why do I know it's a log problem, Pat? What is it about where my missing value is that tells me I'm going to need logs?
The 2n.
It's in the power. If ever I've got a missing number in the power, then I'm going to need logs. So whenever I need to use logs, I need to get that 2 to the n on its own. So here we go. I'm going to multiply by -1, that's nice and easy. And then I'm going to add 2 to the n to both sides and add 2 million to both sides. And here's where we've got the choice. We can log log both sides and then use the third log rule. But if we're feeling confident, we'll remember that the opposite of 2 to the power of something is to use log to the base 2. We can just log to the base 2 both sides. All log to the base 2 asks is, what power of 2 is that? What power of 2 is that? It's 2 to the power of n. What power of 2 is that? I have no idea. That's why my calculator will do it for me. And remember, to get log to the base anything on your calculator, you press F4, which is labelled math, annoyingly. And then is it F2? I think it's F2, which is your log AB button. And you should therefore be able to do log to the base 2 to get the answer to that one. We know, because we've asked when does it equal 2000, we feel we're unlikely to get a whole number. And it's not about rounding it, it's about pushing it up to the next value. Hopefully you can get 21. So you get 20.9 is your value of n, rounded. So the 21st term will be the first term that makes the total exceed 2 million. Right, page 72, and I want to start tomorrow by going through number 7. So have a quick knock at number 2 now, but can I ask you, however far you get, to have a look at number 7 before tomorrow's lesson? Number 7, you can't avoid inequalities with number 7. But there is an inequality rule that we need to remember, which we have to use to make it work. So have a quick go at number 2 now. So S10, sum of the first terms. And to work out R, take a term, divide by the previous term. Should we got that? So please, if you can, make sure you've had a look at number 7, because I'm going to start by going through that one. And there's a particular thing you need to remember about inequalities. Good stuff.